Every day across the globe, commercial vessels navigate unpredictable and punishing oceanic environments while carrying thousands of tons of volatile cargo. This view from the deck illustrates the primary operational problem of the industry, containing massive volumes of explosive, toxic, and highly incompatible chemical materials within a single enclosed floating structure. The solution is kept immediately accessible on the ship's bridge, stored in fire wallets. It is the Chief Officer's Dangerous Cargo Stowage Plan. This document defines a rigid geometric configuration, legally enforced under the SOLAS and MARPOL international conventions. The exact placement of every container is dictated entirely by a deterministic international algorithm, the International Maritime Dangerous Goods Code, or IMDG code. The code operates under a strict dual mandate: protect the lives of the crew on board and prevent catastrophic pollution of the marine environment. To survive a voyage with hazardous materials, the crew must successfully translate abstract chemical properties into exact physical coordinates on the ship. The process of reverse engineering that precise geometry starts here at the port. Long before this container is locked into place on the deck, its internal contents must be translated into the IMDG code's universal regulatory language. The code categorizes all hazardous materials into 9 distinct hazard classes, from explosives in Class 1 to miscellaneous in Class 9. But broad categories cannot prevent a disaster. To apply the rules correctly, this grid fractures into specific data nodes representing individual substances. Knowing a container holds a flammable liquid is useless to a cargo planner. The system requires a unique identifier to trigger the exact algorithmic rules for that specific substance. Within those 9 hazard classes, every dangerous good on Earth is uniquely identified by 2 pieces of information: a 4-digit UN number and its proper shipping name. Standard kerosene, for example, is processed not by its generic chemical traits, but specifically as UN 1223 under the proper shipping name kerosene. Shore-based personnel use these identifiers to cross-reference every proposed cargo against the code's operational datasets. That core is the dangerous goods list. This 18-column database matrix processes raw identifiers into actionable data. Columns 1 through 4 confirm inputs. They lock in the UN number, exact shipping name, primary hazard class, and subsidiary risks like marine pollutants. Assigning that UN number forces raw, unpredictable chemical behavior into a highly regulated data pipeline. Subsequent columns dictate the cargo's physical reality. Columns 8, 9, and 10 determine packaging structural strength. Column 15 assigns emergency schedules, dictating response protocols for leaks or fires. The ultimate destination is column 16, splitting data into 2 distinct tracks: stowage and segregation. Column 16 provides the final positional coordinates. It tells planners exactly how to physically place the container on the vessel. This is also where the system frequently breaks down. Human error often occurs when logistics personnel conflate these 2 terms as a single concept. Failing to distinguish between where a container sits and what it sits next to compromises the structural safety of the entire ship. In this 3D cross-section, stowage becomes a question of physical anatomy, placing cargo based entirely on the ship's specific design, bulkheads, and machinery layout. A vessel can only carry dangerous goods if it holds a document of compliance. This certificate legally verifies the ship's structural capability to handle specific hazard classes. Under the stowage rules, a container labeled "protected from sources of heat" requires a mandatory 2.4-meter clearance from any engine bulkheads, heated fuel tanks, or steam pipes where temperatures exceed 55 degrees Celsius. A clear of living quarters mandate prevents containers that produce volatile or toxic vapors from being placed anywhere near the intakes that draw fresh air into the occupied parts of the ship. Highly toxic or flammable gases trigger the strict on-deck-only rule. They must be kept above the hull to ensure the vapors can disperse naturally into the atmosphere in an emergency. Modern vessels can modify some of these below-deck restrictions by mechanically forcing ventilation, which keeps the air moving and prevents flammable gas pockets from reaching their explosive limit. Stowage is an environmental calculation. It focuses entirely on the relationship between the hazardous material and the ship's physical machinery. Segregation solves a different problem. It defines the required physical distance or structural barrier between two fundamentally incompatible chemicals. Segregation focuses on cargo-to-cargo proximity. The segregation matrix calculates risk by intersecting hazard classes, like flammable liquids and oxidizers. It outputs rigid instructions. 1 is away from, 2 is separated, 3 requires a complete compartment, and 4 demands longitudinal separation. An X warns the planner. It does not mean the cargoes are safe to mix. An X means the planner must abandon the general class rules and return to the specific UN number in the dangerous goods list. Individual chemical traits often override the broader matrix. Segregation acts as the final structural barrier. Even if the stowage parameters are executed perfectly, placing two incompatible materials side by side turns a minor leak into a catastrophic chain reaction. Once the matrices are resolved, the cargo planners translate these abstract parameters back into physical documentation. The data generated by the dangerous goods list populates the dangerous goods manifest. This document maps every single hazardous material to its exact three-dimensional coordinate on board. It is accompanied by the material safety datasheet, which provides the crew with the chemical's occupational hazards and immediate spill handling procedures. Finally, a packaging certificate proves that the physical container enclosing the hazard has passed the rigorous structural testing required for maritime transport. This documentation is a direct, life-saving translation of the IMDG code's algorithm into an actionable map. All of this compiled data is returned to the bridge, where the watchkeeping officer keeps it continuously available. If a fire breaks out or a toxic liquid spills mid-ocean, the crew has no time to run chemical diagnostics. Their immediate response relies entirely on the accuracy of the coordinates locked into the manifest. Cross-referencing that location data with the medical first aid guide dictates the exact tactical response. It determines whether the shipboard crisis is contained or escalates into a fatal disaster. The IMDG code provides the invisible regulatory architecture required to keep the system intact. By processing raw chemicals into strict physical geometry, thousands of lethal variables can safely transit the global maritime commons.